All right, well, without further ado, let me go ahead and get us started today. So welcome back to the SMU Physics Department Speaker Series for Spring 2021. We continue our April series today in its theme of From Subatomic to Cosmic. And in a moment, I will hand things over to Professor Joel Myers to introduce our speaker today, Dr. Kimmy Wu from SLAC. But before we get started, I just want to make some of the usual reminders. So to our audience on Zoom, first of all, welcome. And then remember that if you want to ask a question during or after the talk, write the word speak in the chat window to indicate you want to speak. If it's during the talk, we'll just interrupt the speaker at the next opportunity, like the next slide change to get to your question. Or if it's at the end during the Q&A, we'll use the order in which the word speak appears from people to set up a speaker queue, a queue for that. You're only going to be able to speak when called upon by a moderator. This helps to avoid the hot mic problem we all have on Zoom meetings. And one last reminder, this event is being recorded and simultaneously live streamed on YouTube. So hello to our 4 viewers on the YouTube live stream as well. All right, let me hand things over to Professor Joel Myers to introduce today's speaker. Joel?
All right, thanks, Steve. So we're very happy to have Kimmy Wu speaking today. Dr. Kimmy Wu is an observational cosmologist going after imprints of the early universe on the cosmic microwave background and in large-scale structure. She builds and collaborates with teams to write software to achieve this goal using data from state-of-the-art millimeter wave telescopes, such as the South Pole Telescope SPT and the BICEP Keck array. To break new ground, she's involved in planning the next generation ground-based CMB telescope or CMB survey, CMB S4, for which she is one of the working group leads for the search for the B modes coming from primordial gravitational waves. Prior to SLAC, Kimmy was a KICP fellow at the University of Chicago. And before that, she was a Croucher fellow at UC Berkeley. She earned her PhD from Stanford and conducted her undergraduate studies at the University of Michigan, Ann Arbor. So with that, I'll pass it over to Kimmy, and we're looking forward to your talk. Thanks, Kimmy.
Hi, everyone. Thank you for joining today's seminar, and thank you very much for this opportunity for me to share about some of the latest results from the 2 experiments that I closely work with, BICEP Keck array and also the South Pole telescope. So I'll be giving some background on this measurement and also some details of how we improve our primordial gravitational wave constraints using this technique called delensing. So this picture here is a photograph of the dark sector lab view at the South Pole. So this is where the 3 telescopes observed from, and this is a military plane that carries both people and cargo to the South Pole for operations. So let me switch slides. That works. So I will just give you all an outline of this talk. So we have a rough idea of where we're going in the next 50 minutes or so. So I'll give a brief overview of inflation. So that's a paradigm of the early universe that we aim to test with observations of the cosmic microwave background, and also the lensing of the microwave background. That's a very important component of this work that I'll introduce called delensing. Then I'll introduce the characters of the 2 telescopes of BICEP Keck array and the South Pole telescope, from which I draw the data for my analysis. Then I'll go into some details of this analysis and give a brief outlook of what the next steps look like from this combined experiment, and also our next generation foreground ground-based CMB experiment, CMB S4. One thing I'd like to highlight on this slide is the background picture. So this is taken from the back of the South Pole telescope, and really the really cool thing is the 2, it looks like a rainbow around this 2 halo, you can see. So this is a double sundog. So the physics behind it is very similar to rainbows, but instead of reflection off of water droplets in the atmosphere, it's a reflection off of ice crystals. Alrighty, so inflation and CMB. So CMB is my observable, and it's really cool because it's sensitive to physics of both the early universe and the late universe. And this is a very familiar illustration of the history of the universe. And at early times, inflation occurred, during which the universe underwent a near exponential expansion. And after some 400,000 years, the universe was cooled enough for neutral helium and hydrogen to form. And that was when the CMB was formed. So photons were able to free stream from this fluid of elementary particles. And since then, stars and galaxies were formed, and the CMB photons, as they traveled to us, their paths got deflected by the intervening gravitational potentials. And that's what CMB lensing effect encapsulates. So inflation generically predicts the existence of gravitational waves. And this talk will be about looking for a signature on the BMO polarization of the CMB. And one key aspect of it involves understanding the CMB lensing effect, and that is a late universe of occurrence. And tying together these two aspects of the search of the BMO polarization and CMB lensing is the need for delensing, which I will introduce in a few slides. So first of all, let's walk through a few simple steps to connect how we observe and how we determine predictions from inflation from the observation of the microwave background. As I mentioned already, inflation generically predicts the existence of primordial gravitational waves. So we can write down perturbations of the metric at inflation. So they include scalar, vector, and tensor perturbations specifically. So vector perturbations are usually not sourced in simple inflation models. And even if they are sourced, they decay at superhorizon scales. So here we can safely just consider tensor and scalar perturbations. And during inflation, these perturbations are stretched out into classical waves. So they form gravitational waves. So this is a cartoon of the plus and the cross stretching of spacetime. So it redshifts and blue shifts photons. These are what the blue and the red arrows denote. Then while the scalar perturbation gets stretched out into density waves, like sound waves, and they are the ones that provide the seed for structure formation, okay? So in terms of their signature on the CMB, gravitational wave create conditions for the so-called the E modes and B modes, like your ENM, in magnetic and electric fields in your ENM. So the magnetic fields are divergence-free, and the electric fields are curl-free. So these are similar bases to your E and B fields in ENM, although they are not exactly the same. Whereas the density waves here create conditions only for E modes. Okay, so as you can see, when the CMB is formed, if you observe B modes, it can be directly linked to the tensor perturbations at inflation. And so it's a good handle on these perturbations at inflation. And CMB physicists like to parameterize our tensor perturbations relative to the scalar perturbations. So we call it the tensor to scalar ratio, R. So essentially it is the tensor spectrum amplitude to the scalar spectrum amplitude at a specific pivot scale. And if R is somewhat large, then it actually tells us that the energy scale at which inflation occurred it's near God's scale physics, where then it would land support for the idea of force unification. And it is also a regime that's so high energy that we don't typically get to probe with ground-based accelerators. So it's an extremely interesting way to be able to just explore and probe what could be happening at that energy scale. So that's a leading reason of why we want to look at for the signature in the B modes of the CMB. In addition, for model builders, if you want to write down what the inflationary potential look like, different R, tensor to scalar ratio value, are predicted by different models of your inflaton potential. So this is a plot of the R versus N sub S parameter. So N sub S describes the tilt of the scalar spectrum shape. And as we continue to put better upper limits on R, we can rule out classes of inflationary model potentials. So it helps our theorist friends to continue to probe space of inflation framework that are allowed by nature. All right, so if we are so eager to look for this B mode in the CMB, why haven't we done that already? There are a few reasons, and one of them is that it's a challenging measurement for the following reasons. So the first one is that our primordial gravitational wave B modes are very faint. So what I'm showing here is a power spectrum of the CMB in the temperature and anisotropy, so temperature fluctuations across the entire sky, and emo polarizations, and for the gravitational wave generated BMO polarization spectrum for two values of R equals 0.1 and 0.01. Now, and just quickly for this, the y-axis is what we call the angular multiple. So it gives you a sense of how spatially how separate these different what we call modes, spherical harmonic modes, are separated on the sky. So like your wave numbers, if L is smaller, it actually tells you a larger spatial scale. And if L is larger, it denotes a smaller angular separation on the sky. Now, as you can see on this plot already, these are on the y-axis. It denotes the fluctuation power, and it is on log scale. So the gravitational wave beams are orders of magnitude below the temperature and isotropy power spectrum. And to give you a sense, the temperature and isotropy spectrum are now very well measured. We have pretty good measurement of the E-mode polarization. But really, we are just at the frontier of being able to measure some B modes and not the primordial gravitational wave generated B mode quite yet. And comparing that to the mean temperature of the CMB, which is around 2.7 Kelvin, these fluctuations are differences from the mean of less than a part in a millionth. So these are tiny tens to hundreds of nanokelvin fluctuations. So we need very sensitive detectors, and many of them, to be able to make really good measurements of these polarization fluctuations. So that's challenge number one. It's a very faint signal. To, again, give you a sense of where we are in terms of how well we have constrained are from B mode only measurements. Our current upper limit on R are less than 0.07. So the like 95% confidence level line is slightly below this R equals 0.1 line. And if you combine that with temperature and E mode polarization measurements from Planck, and also the BICEP Keck B mode measurements, the upper limit on R is slightly tighter to R less than 0.044, so about halfway between this 0.1 and 0.01 line. Now, one thing I'd like you to pay attention to is this particular bump at L of around 90. So this is about 2 degrees on the sky. For scale, the moon across is about half a degree. So these are fluctuations that peak at a few moons diameter. So these are what fluctuations spatial scale that we look for. And that has implications of how we design our telescope to focus on the peak at around 2 degrees. Alrighty, So that's challenge number one. B modes are very faint. Challenge number two is that we have other sources of B modes in our galactic neighborhood. So also generate B modes in the millimeters that confuse us. So the two main sources of polarized foregrounds are from synchrotron radiation and polarized dust emission. And what I'm showing here is no longer a angular spectrum of the sky. It's a polarization amplitude as a function of frequency. So thankfully, the thermal dust and the synchrotron radiations, the polarization has a different frequency spectral dependence compared to the CMB, which is close to a black body. And really the most precisely measured black body that we have in nature. Then what that means, though, is that by measuring millimeter wave sky in multiple frequency bands and fitting the different models of these different components of the sky, we can tease out the CMB component from the dust and the synchrotron emissions. To give you a sense of how large these foregrounds are, here I have sketched in the dust foregrounds at 150 gigahertz for about 1% of the sky as one of the cleanest patch of foregrounds in the sky. So we already know that foregrounds overwhelms the primordial gravitational wave generated B modes because our upper limit is below this R equals 0.1 line. So we need to clean our foregrounds in our measurement, and we can do that by having multi-frequency observations of the millimeter wave sky. And thirdly, we have a third challenge coming from the lensing of the CMB. As I mentioned already, the CMB, when it was first formed, it has to travel through the intervening gravitational potentials to get to us as the large scale structure was forming. So what we observe is a lensed version of the original unlensed field, and you can encode the amount of deflection by the gradients of phi here. So phi is the what we call the lensing potential, and it is the weighted gravitational potential integrated along the line of sight. So how does this create a B mode? So let's say in your original CMB, there were no tensor perturbations. So all you have sourced from your primordial perturbations are just E modes. So you denote it by this co-free polarization basis. Now, as this polarization E modes travel to us, these vectors get shifted one way versus the other, depending on the line of sight gravitational potential. So you might then have a slightly distorted E mode. However, as you can see, you can no longer describe this pattern by a pure E mode. So you have to describe it as a combination of E modes and B modes. In terms of map space, this is usually more helpful to illustrate its effect. This is what lensing, the impact of lensing on CMB maps. So what I've shown you here on the top is your temperature and isotropy, E mode polarization, and B mode polarization. So here I'm assuming we don't have any primordial B modes, and here the color stretch orders of magnitude different across these three panels. Now I'm going to pass through the CMB temperature and isotropy and polarization vectors through the same lensing potential simultaneously, and this is what they look like. So you see that the temperature and E mode polarization get shifted a bit here. So they get magnified, demagnified at places, and then out pops these polarization B modes. So that's the effect of lensing on CMB polarization and generate B modes. Now, I want you to focus on the bottom panel. I'm going to overlay R equals 0.1 B mode fluctuation on top of this lensing B modes. Okay, and that's the difference. And so you see a larger scale fluctuation because it peaks at around 2 degrees. For scale, each panel is about 8 by 2 degrees. And your eyes can barely make out the difference before and after I overlay the R equals 0.1 fluctuation. And that said, on top of this, we have foreground fluctuations that are brighter than R equals 0.1, and we know that the primordial B modes are going to be below this. So it's a challenging signal to dig out, and we have to clean out this lensing B mode fluctuation. So put this back together under the power spectrum. Here I have added the lensing B mode power, overlaying the foregrounds and the expected primordial gravitational wave generated B modes. So if as we keep including improving on our upper limits on R, we know that lensing is going to become a dominant contamination to our measurement. So we need to delens in order to get to our primordial gravitational waves signature in the B mode polarization of the CMB. Now, just a quick summary of this intro part. I have walked through quite a number of things, but the key here is that we want to use B mode observations of the CMB to constrain our one key predictions from the early universe of the inflation paradigm, that we expect there to be tensor perturbations and that it produced primordial gravitational waves. And being able to probe that amplitude will tell us about the energy scale of inflation. And there are a few contaminants to our B mode observations, and one of which is the lensing B modes. And we need to delens in order to reduce its impact on our primordial B mode measurement. And that is a new frontier to our B mode measurement analysis. And that's what I'm going to focus on today. Now let me introduce our telescopes. So one potentially new activity to the audience is that I'm going to use the poll function to engage you all in a bit of Q&A and multiple choice questions. I will be showing the first question soon, and that is about why the South Pole is an excellent site for millimeter wave observations. So what I'm showing here is an aerial photograph of the South Pole station area. So this is the station. This is the dark sector lab area. So the photo I've shown in the front page is taken from this side, looking towards the telescopes. Now now I'm gonna have the poll for all of you. The question is, what makes the South Pole so good for millimeter wave observations? So I have 6 options, and you can choose multiple responses you can choose multiple options as your answer. And let me launch the poll, and I'll give you all a minute to respond. Let's see. Let me do this, and it should work. So A is that it's great because it's a desert. B, it has a high elevation. C, it has little light pollution. D, the sun only rises and sets once every year. And E, it has great seeing. And F, penguins.
Looks like you're getting trolled, Kimmy.
It's the best. All right, another 15 seconds. For those who haven't responded, it's your last chance. Okay, 3, 2, 1. I'm going to close the poll. Can you all see the results?
I certainly can, yes.
Oh, okay, let me do this. Now I think you can all see the results of the poll. Yes, yeah. Okay, great. Thank you for responding. For the uniqueness of the South Pole observing sites, first of all, it is extremely dry. So geologically, it is a desert. And that is helpful because for millimeter wave observations, we want to have as little water vapor in the atmosphere as possible. So the best really is to go to space or fly a balloon to avoid the atmosphere. But if you're going to do ground-based observations, you want to go to the driest places on Earth. Then it has high altitude. So that's another advantage because that means the amount of atmosphere above you is thinner. And a third one that I list here is that the sun actually just rises and sets once a year. So what that means is that you don't have the daily heating and warming, heating up and cooling of the atmosphere that would degrade your observing conditions. So unfortunately, it's not because of penguins. I know it's oftentimes a favorite answer for many people. I wish there are penguins at the South Pole so that I can see them and watch them. But it's actually too far away from the coast of Antarctica, so we just don't get to see penguins at the South Pole. Now, with that. That's some of the key reasons for us to observe from the South Pole, and I'll talk a bit of the details of the instrument designs, of why they are optimized for making these observations and for delensing. So the BICEP Keck array series of experiments are what we call small aperture experiments. So I was in a small team that helped design and build BICEP 3. So this is a picture of BICEP 3 from the top of the observatory, and this is the focal plane of BICEP 3, and I can almost wrap my arm around this receiver, this vacuum jacket. So the aperture of it is about 30 centimeters, so it's about this large. What that means is that its resolution is slightly low. It's about a quarter degree on the sky, but it's sufficient for resolving the 2-degree primordial gravitational wave generated B mode bump that I have shown you. And the advantage of having a slightly compact camera is that you can then do a lot of manipulation of the whole telescope. You can rotate it, can shift it one way versus the other, and be able to cancel various kinds of systematics that one might vary about for this kind of measurements. BICEP array is essentially 4 copies of BICEP 3-sized receivers, and for each of these tubes, so these are still Keck arrays. We are in the process of upgrading them into larger receivers, but this one is our first BICEP array receivers on the mount. So for each of these receivers, we outfit them with different optics and different detectors that are sensitive to different bands. So each color here denotes different frequency bands. So these are windows that are available to us to observe from the ground, from 30-40 gigahertz to 220-70 gigahertz. So with the different frequencies, then we can do the component separation, the foreground cleaning better. So these recap what I said in words. Then I'll introduce the South Pole telescope. It's a very different style telescope compared with the BICEP Keck array telescopes. So we have a person here for scale. So instead of being able to wrap her arms around the whole telescope, this is a 10-meter structure. This dish is 10 meters across in diameter. So what that means is that, and in our jargon, we call it a large aperture telescope, very creative. And that helps us to have really high, really fine resolution millimeter wave observations. So for SPT at 150 gigahertz, the resolution is around 1 arc minute. So contrasting the BICEP Keck receiver's resolution of half a degree, it's a factor of 15 difference. And it has produced one of the largest deep CMB polarization maps in sub-degree scales so far. So it's also with a lot of detectors packed in its receiver. So it's the receiver cap, and the camera actually sits here. We can make really deep observations with this telescope. To give you a sense of the quality of the images from SPT, I cut out the full sky observations from Planck. I left a 50 square degree patch. So this is Planck observation at 143 gigahertz. This is the size of the moon for scale. And now I'm going to flip over to a SPT pole image at 150 gigahertz. On the same patch of the sky. So you can see that in terms of noise levels, it's about 6 times deeper. And in terms of angular resolution, it's about 6 times finer. So you see that with the about 1 arc minute resolution, we can observe point sources that are all confusion limited in the Planck map, and also galaxy clusters. And as you can see, BICEP Keck and SPT observes different regimes of angular scales. So if you are to place data points on this plot, you kind of know which regime would be good, well measured by BICEP Keck, and which regime won't be able to be reached by BICEP Keck. So now I'm going to overlay the B mode spectrum with some actual measurements. So because of the differences in resolution, BICEP Keck cameras can't really observe the small scale fluctuations of the CMB that SPT can do well. Now, what that also means is that we have complementary information from both of these experiments. And it is moving forward, we find that we have good synergy in combining these two data sets, especially for delensing. So we actually had our first South Pole Observatory meeting in the before times, when we can still have collaboration meetings in person. And we formed this umbrella organization, and we are committing to sharing data for current and ongoing data analysis. And really, the key to take away from this photo is we have T-shirts, so we are very organized. Now, delensing BICEP Keck B mode maps, and I'm gonna share some details on that. So the first question is, how does our lensing signals, in the power spectrum, lensing B mode is larger than our current upper limit on the R estimate, but how does it enter our uncertainty of the R measurement? So very, very simply, our sigma R, the uncertainty of our R measurement, is proportional to our signal variance, which has contributions from lensing from our galactic foregrounds, and also have contributions from our primordial gravitational wave B modes if it's non-zero. And then it has noise variance that comes from the instrument noise. So delensing for R, really what the key there is that we want to reduce the lensing sample variance, the lensing contributed power to our B mode measurement contributed when we measure R. So we want to reduce this solid black line in our BB measurement. So how do we do that? The idea is rather straightforward. Lensing B modes come from lensing of our unlensed E with a lensing potential phi. So if you have a cartoon phi like this one as a 2D Gaussian, you can calculate what your lensing B mode look like. And this is, let's say this is your input E mount. This is what your lensed B mode would look like if your lensing potential looks like this. Now with a lensing B mode template, then you can subtract it from your observed B, or you can cross-correlate it with your observed B. And with some model of what the cross spectrum would look like, you can then extract your lensing contribution to your B mode spectrum measurement and be able to constrain your lensing B mode contribution and reduce the uncertainty of the R measurement. So here in this observed B box, I have also overlay other larger angular scale fluctuations that are not lensing B. So from CMB measurements, we get the E modes and we have our observed B. So one question is, how do we get a lensing potential estimate? So one way to do that, to extract it, is to use the lensed CMB observations. We can do CMB lensing reconstruction to reconstruct the lensing potential. For this analysis of delensing the BICEP Keck maps, we use a dark matter tracer, which is the cosmic microwave background, to trace our lensing potential. So the CIB, the cosmic infrared background, are emissions from the dust around dusty star-forming galaxies that has a redshift kernel that peaks around LF 1 to 2, mostly 2. And it turns out the CMB lensing potential redshift kernel peaks around redshift of between 1 and 3 as well. So these two tracers of gravitational potential ends up having rather good cross correlation. It could be as high as 80%. So you can use the CIB, so this cosmic infrared background, as a CMB lensing potential tracer, and use it to deflect your E mode map to get your lensing B template. As I mentioned, we can also reconstruct phi from the CMB itself, but the signal to noise is not great currently, but it will be soon getting better, and we're actually almost there with our data in the can. So that's our inputs. We have our CMB maps. We have our CIB as the phi tracer. We want to also combine our E modes from not just the BICEP Keck experiment, also use SPT pole and Planck E modes for the lensing template. So what I'm showing here is the BICEP Keck E mode 2D angular power spectra average across 10 simulations, and the equivalent spectra from SPT pole and Planck. The rest recall denotes the same angular scales on the 2D plane. And because of the difference in angular resolutions, both SPT pole and Planck can observe these higher L, smaller angular scale acoustic peaks in the E mode that BICEP Keck has little signal to noise to see. And it turns out that having these higher L measurements in E mode is important for us to form a good lensing B mode template as well. And here I'm showing a combined and unifiltered 2D power spectra from the 3 experiments. Now let's make the lensing template. We have our polarization Q and U maps. So these are the Stokes parameters which we can transform to our E mode map. So this is an example of a lensed Q map. We have our phi tracer, so we can undeflect our phi tracer, our lensed Q map by our phi tracer. So that's the undeflected by the negative gradient of phi map. You can barely see the difference between the two, but the modes do shift a little bit. Then you can subtract your undeflected Q map by the lensed Q map, the first map. And what remains are the modes that are generated by lensing. So that's the differenced map. And it's really faint, so I'm gonna zoom in the color stretch so that you can actually see the modes. So that's the input to our lensing template, and we do the same thing for the Q maps. Then from the QU maps, then you can calculate what the B mode power spectrum look like from the lensing template. So connecting these input raw maps, we generated lensing template to an R analysis. First, I'll introduce the BICEP Keck R analysis approach. Then having delensing, incorporating delensing to it will be a straightforward extension. So the BICEP Keck R analysis takes a few data inputs. So we need maps from this patch of the sky. So of course there are observations from the BICEP Keck array telescopes themselves. So including 95 and 150 gigahertz observations. These are QU maps at 150 gigahertz. Then we also use satellite experiments maps, including Planck and WMAP, across a wide frequency range. So these are Q and U, and the higher frequency ones, for example, here are dominated by galactic dust. So we effectively use these external maps to constrain our foreground, galactic foreground contributions. So with these input maps, we form auto and cross spectra of all of them, and we have input maps of, without delensing, we have 11 input maps. So you can do a quick arithmetic and be able to calculate how many auto cross spectra there are. And this is a sample of them. And because don't want your eyes to get dizzy, I zoom in two of the panels of the BICEP 95 gigahertz and 150 gigahertz auto spectrum from the data. So the band powers. So these form our input data vector to our likelihood. So in the likelihood, you compare your measurements to your expected theory spectrum. So the red line is a theory expectation, including dust. And the black line is a theory expectation without dust. So our theory expectation has a description of a dust and synchrotron component for foregrounds. And then you have a band power covariance matrix that describes the covariance of these band powers across all of these different frequency bands. And you can calculate the likelihood of each model against your data. And from that, you can draw a posterior of each of these model parameters that are besides the foreground parameters. There's also R and the lambda CM expectation of the lensing B mode amplitude. And that's how we extract the posterior of, for example, a distance sync. There's a few extra parameters subpanel that I didn't show here. And the black line is where the upper limit of R equals of R less than 0.07 comes from. Now, so this is a BICEP Keck R analysis without delensing. To add delensing, I simply add to this set of maps the extra lensing templates that I just formed using the combined BICEP Keck SPT pole and Planck QU maps, so the E modes, and the CIB as a flight tracer. And I repeat the exercise of forming auto and cross spectra of all of these maps. And now I have a total of 78 auto and cross spectra, and this is a subsample of them. So the LT ones are the ones that include the lensing template. And then we have a likelihood, and you can then draw a posterior of your foreground parameters and R, now knowing the lensing contribution given your estimate of the lensing template. And now, in this slide, I show the R posterior without the lensing for the what we call the BK14 data set. And I'm gonna set you a poll question of asking you to predict which of the following scenarios do you think best describe the post-delensing marginalized R posterior. So let me start the poll now, and we'll go through the options as you have a chance to decide on what you think will happen. So there are 4 options. The first one is that the uncertainty, the posterior uncertainty, will be reduced, and your peak marginalized R value would be reduced, will be lowered, go this way. B is similar in terms of uncertainty, but the peak is going to shift up. And then C is that your uncertainty will be enlarged, and you'll get a lower peak R. And D is that similar in the uncertainty change, and your peak R will go up. Let's see, I'll give you all 10 more seconds. 5, 4, 3, 2, 1. Now I'm going to end the poll and share the results. Alrighty, so most people think that the uncertainty will be reduced, but the peak of the R is going to shift up. Let's find out what we find. So the red is still the same curve as before, and our post-delensing R posterior has our uncertainty reduced, so most people get that. But our peak R value also actually shifted down a little bit. Our upper limit on the R post-delensing reduced from 0.09 to 0.082. One thing I like to highlight, it's actually folks have really good intuition in terms of whether the uncertainty is going to increase or decrease. And in terms of how the peak changes, from our simulation, we find about a third of the realizations will have a higher peak R, and about 60% of them will have a lower peak R. So it really depends on the exact noise fluctuations. So how the band power shift up or down in the particular realization that we observe that determines the resultant movement of the peak. So let me stop sharing here. And one interesting breakout panel for the delensing result is this one. So in the previous R posterior that I've shown, I have the lambda CDM expectation of the lensing beam mode fixed. Here we allowed it to flow. So the red is without delensing, the black is with delensing. And you can see this interesting breaking of degeneracy between R and A lens. So the posterior between R and AL get much flatter, and you're able to constrain the A lens amplitude much better with your lensing template measurement. And let's see. I think I'm still sharing. That's good. So we can ask in another way besides looking at the R posterior how much we improve sigma R. So the R posterior, as you know, could be impacted by the exact noise fluctuation of the one realization. So to remove that, we can use our simulations to give a measure of sigma R. So the way that we estimate this is we take 499 simulation realizations, and then we draw from them our maximum likelihood R. And from the distribution, we estimate the width. So these are all R equals 0 simulation realizations with and without delensing. And we also run a case where we have perfect delensing. We know exactly what the lensing modes look like in all of these realizations. So what we find is that if we have perfect delensing, we reduce sigma r from 0.024 to 0.018. So that's about a 26% reduction in sigma r. What that also means is that about 26% of your R uncertainty comes from lensing for this data set. Of course, our phi tracer and our E modes are not noiseless, so we don't estimate the perfect lensing template. So for this analysis, we reduce sigma r by about 10%. And I'll just and that's the histogram fit from the simulations that describe this analysis. And it's cool because it's a first demonstration of reducing sigma r reduction through delensing. So what's some of the current limitation and how can we improve that? So the first thing is that our beam of variance is dominated by foregrounds and noise. So even if we perfectly delens, remove all the lensing beam modes, we do not improve sigma r very, very significantly. But that picture will be changing very quickly. Our ability to constrain our galactic foregrounds is improving with deeper and deeper observations in all in the range of millimeter wave bands, and lensing is becoming more and more important. So once we're in that regime, we will need a better phi tracer. Our CIB map is, while it's a very good, has a very good correlation with the lensing potential, it doesn't have a perfect correlation. And especially for the large scale, large-ish scale phi CMB lensing potential, which sources a lot of the lensing B modes, the CMB derived, CMB reconstructed phi with our low noise CMB polarization measurements will do better very soon. So I'm going to skip key takeaway and talk about how to get a better phi. So there are two key approaches. One is that we need to make deeper high resolution CMB polarization maps. Two is we need to extract our lensing information more optimally. So to do that, we built bigger and better experiments, and SPT3G has a larger focal plane, and we pack about 16,000 detectors onto that focal plane. So it's about an order of magnitude increase in detector counts compared to the previous generation camera SPT pole. The SPT3G and BICEP array are observing overlapping regions that are highlighted by the red rectangle here. So our ongoing observations on the main CMB field are resuming now that the austral winter is starting. And our noise levels are on track to match our expectations. Our first science result actually just came out a few months ago. So from our 2018 observations, we made E-mode polarization measurements and temperature cross E-mode polarization measurements. So this is work led by Daniel Dutcher and Leonard Bocanol. From this, you can extract lambda CDM parameter uncertainties. In particular, I like to highlight the H0 measurement. So the uncertainty on this H0 measurement is actually similar to a recent XDR4 release, and now we have an independent measurement of H0 from Planck as well. And we have explored extensions to a lambda CDM model with this data set, and the summary can be found in these two recent papers. Now back to lensing. We have ongoing work to reconstruct the lensing potential using the CMB observations by SPT3G. So this is a simulated map made by Zhaodi, and on the 1500 square degree footprint here. And just from this data set from our 2018 observations, we expect that the cosmological parameter constraints will be either comparable or slightly better than the final SPT pole depth for the lensing map already. So that's plenty exciting. And with this phi map, we can use the lensing potential to construct the lensing template for delensing. So that'll be exciting. And in terms of more optimal extraction of lensing information from the data, we are exploring this Bayesian approach of analyzing the data, and Marius demonstrated with this Bayesian approach, we will improve the lensing amplitude constraint from the CMB lensing map by about 20%. So that's for SPT pole noise levels, and looking forward for CMBS4 noise levels, it will be even more improvement in terms of being able to get better signal to noise of the lensing reconstruction and the lensing template extraction. Just 2 words about expected constraint on R given the BICEP Keck and the SP3G data sets. So this is a projection of uncertainty on R as a function of time, given the time of data in the can. The tightest published sigma R is from BK15, so it's about 0.02. It's at this level, and there's some analysis delay. And also because of COVID, our deployment of some of these receivers are delayed. So we expect this curve to uniformly shift to the right a bit. But when both of these experiments get to its projected full depth, we expect to be able to improve the R constraint by more than a factor of 2.5 with delensing. And that's a drastic improvement compared with what I've just shown you as from the first demonstration of delensing, which just improved sigma R by 10%. And the reason for that is because by then we'll really be lensing limited in our measurement, and delensing will help a lot. So I'll finish by having one slide, just giving a shout out to our next generation ground-based CMB experiment, CMS4. So we'll have telescopes at both the South Pole and the Atacama Desert. We'll have almost an order of magnitude, maybe even more than an order of magnitude increase in the number of detectors, current generation experiments. And a D survey will be dedicated for the search of R, and there will be a Y survey that will be very exciting for lensing cross correlations and various multi-messenger astronomy sciences. And I'll leave some projection numbers here. They're interesting for various reasons. Okay, I think I might be running a bit out of time, so I think I'll just leave my summary slide here and take questions.
Okay, yeah, thank you very much. We'll give you a little virtual applause here.
Wow.
All right, so let's go ahead and open this up to general Q&A. If you want to ask a question, just type the word speak in the chat window and we'll get you unmuted. So we'll give people a few seconds there to type and hit enter. And I have some questions just to stall. Great, Tom, let me get you unmuted here. Go ahead, you should be able to unmute.
Yeah, I missed something fundamental. If the uncertainty in R gets down to about 3^10⁻³ what do I then learn about inflation?
Yeah, let's see. So this is not the best plot for this, but it illustrates the idea. Oh, yeah, so I can't move this. So if you look at the legend of this plot from the Planck paper, different inflationary potential shapes predict different R values. So for example, if we look at this yellow line here, it's a phi square potential. And by now they are well ruled out by the upper limit of BK14. And we'll be producing even tighter and tighter upper limits. So at sigma R of 3 times 10 to the minus 3, so we're talking about upper limits that are around here. And I'm sure there are some models that will be that will be interesting kind of around that regime and might be ruled out. But really the target from CMBS4 is well motivated in that given our measurements of N sub S, some of the what my theorist friends will point out is that some of the more natural R value should be above, should be around 3 times 10 to the minus 3. So if the sigma R is 5 times 10 to the minus 4, at 2 sigma, you'll be able to rule out those models or be able to make some a significant detection. So that will be extremely interesting. Of course, we're always ready for surprises. So we'll find out as we make deeper measurements.
So these are all, I know nothing about these models, but I just assume that, well, they're models with various degrees of assumptions. Could you make an editorial comment if you just sort of made a quasi-model independent extrapolation from all these models? When does R become interesting? I mean, theorists pump out models weekly. That's what they get paid to do. But
I really think the target that CMBS4 is targeting is well motivated. It has minimal assumptions, and it doesn't require multi fields or. It really is because from a single field model, given this N sub S, this is what one would naturally expect. But we could be surprised, and we have been surprised many times. But maybe Joel can speak into this more than I have.
Yeah, the other big thing that divides these classes of models is large field versus small field. That's not a sharp dividing line, but it is a thing that people use to motivate this particular target. And the distinction here has to do with how far the scalar field moves through field space as it does its rolling and its potential to generate inflation. But I think Kimmy covered it pretty well, that the people often like to use this term textbook models. All of these textbook models tend to predict a value of R that would be detected by CMBS4.
Okay, all right, thanks.
Okay, next up we have Krista. All right, Krista, you should be able to unmute.
Hi, Kimmy. My question is about the cosmic infrared background that you use for your lensing template. You showed the plot, and in the plot there were multiple different curves for what looked like different mass regimes of the galaxies. So I'm a little curious, when you build the delensing kernel, do you make, are you making an assumption about the mass of the galaxy based on its infrared luminosity, or assumptions about the mass to light ratio in those galaxies more generally?
No, so this cross correlations from this Planck paper do have some influence on what the halo mass and so on and so forth of the CIB emissions were. But then in terms of for its utility for delensing, we simply empirically measure its cross correlation with a CMB lensing map from Planck, and use it as an integrated deflection field. So with the phi that I derive from the CIB, then I calculate what the undeflection vector field should look like given the gradients of the tracer field. So I do not build I do not rely on a model of the emission the CIB, so the mass to its light, and as a function of redshift knowledge. But that's a very good question.
Oh, give me 1 second. Krista, if you want to unmute and follow up, go ahead.
Yeah, I was just going to say thank you, but
Okay.
I stopped trying when I was forbidden, so.
Yeah. The pro tip at the end of this long pandemic year is don't mute yourself until you're ready to cede the microphone, right? So.
Right.
All right. Thank you, Krista. Next up, Bob Keogh. Let me get you unmuted. Give me 1 second here. And now I seem to have lost you, Bob. Oh, there we go. Okay, go ahead, Bob.
Okay, thank you. That was a very interesting presentation. Thank you very much. I had a question, really just wanted to understand a little better something that you said, and I think it was on slide 42. It went by me and then I realized a couple slides later that I wanted to know it better. Okay, so yeah, so this point about the galactic foregrounds, could you elaborate on that a little bit? And in particular, is there anything that can be done about it, or yeah? Yeah.
So this talk is mostly about delensing. So I didn't talk very much about galactic foregrounds impact. So essentially, as much as lensing contribute to the uncertainty of R, foregrounds also do. So all of this power that I've shown in, for example, this slide. So we make a power spectrum measurement. So at each angular multiple, for each frequency band, we have a summed effect of the lensing, the foregrounds, and the primordial B modes if they are non-zero. So essentially, the uncertainty on R has all of these contributions, and to reduce the impact from galactic foregrounds, we do multiple frequency observations and fit the model of the foregrounds all of the auto cross spectrum. I really skimmed that part because that's not quite the focus, but it's rather simple. So we have the measurements has the cumulative effect of the lensing, the galactic foreground components, and for different foreground amplitude and various parameters that control its shape and brightness, it will predict a different level of this red line, which describes the foreground and the lensing B modes. And essentially, we compare our measurement with the model. So the model includes the foreground component for all of these band power measurements, and to extract a likelihood. So for example, so we have constraints on the amplitude of dust and synchrotron as well that I gloss over.
But is there, and I think that's all been done, and then you still lead into the situation that you say on slide, I guess, 43.
Oh, yeah.
Is there anything further that can be done?
Yeah. So by having deeper observations in frequency bands, either that we haven't quite have deep observations yet, for example, the 30-40 gigahertz. Here in this projection plot, this first dip here comes from, I believe, if I remember correctly, comes from having the 30-40 gigahertz BICEP array receiver turned on. And that's a band that so far we've been relying on satellites such as WMAP and Planck to constrain our synchrotron component. But with the BICEP array that has more detectors and be able to make lower noise maps in those frequencies, we're able to constrain the synchrotron component better. And the later dips here come from having the BICEP array new receivers from 90, 150, and 220 to 70 gigahertz. So by making deeper maps, we can reduce foreground uncertainty. And that's when delensing become dominant, and the lensing uncertainty becomes dominant, and delensing will really have a big impact.
Thank you. Okay.
All right, great. I think we have time for one more comment or question. Tom, you had a comment, so let me get you unmuted. Go ahead.
Yeah, I just had one quick technical question. You take your data at a variety of frequency bandwidths. Are these the frequencies that you really want, or are these just the frequencies that are technologically capable or available, I should say?
Yeah. So technologically, we can make detectors that go even beyond 270 gigahertz, and those have been deployed to observe in space. Mostly for ground-based telescopes, we cannot, the atmospheric window for these for those frequency bands got really opaque, and that's why we oftentimes don't observe from the ground in those frequencies. It become a very inefficient band to observe. So it's not. I would say it's not completely. Yeah. So we can make detectors in those frequencies.
Okay, great. Thank you.
All right. Well, with that, thank you very much. This was a wonderful presentation. I really appreciate you taking the time to speak with us today.
Well, thank you for having me.
Yeah, no, and Joel said, great talk. He always has commitments around 5 o'clock that he has to bolt off for. But I think on that positive note, let's go ahead and close out the event. So Kimmy, have a wonderful afternoon, and to everybody else, enjoy your afternoon, evening, or whatever other time zone appropriate statement is needed. So thanks. Bye, everyone.
Bye.